Hey everyone, I'm Param, and I'll be introducing Nonparametric Bayes today alongside my colleagues Andrew and Orian. This lecture was heavily based off of work by Tamara Broderick and Michael Jordan, so check out their lecture series below. Let's start by breaking down our terminology.
This lecture assumes you're familiar with the Bayes rule, which relates to the posterior of model parameters given data to the prior of the parameters multiplied by the probability of the data given those parameters. For example, when building a model that clusters our data based on its proximity to cluster centroids, we want to maximize the probability of the centroids we pick corresponding to our data so we know we made the best choice. For multivariate Gaussian distributions, these cluster parameters could be comprised of a mean factor and a covariance matrix.
But what if your clusters are seemingly infinite or unbounded, such as in social networks or web pages where there's always a link to another page, or genetic ties between species where you could always discover something new? Modeling this is what we're laying the foundation for today. First, let's recap the finite model. So we have some data with points that are real vectors, let's call them x, with class labels y. For simplicity, say there's only binary possible values for y, so we'd want to pick between two clusters. To simplify further, let's assume each cluster has its own means somewhere on the grid, but all clusters have the same covariance matrix. We denote pi j to be the probability of a point belonging to class j, so naturally all the probabilities add up to 1. Now, how would we craft a prior distribution for, say, pi 1? We could just randomly pick a probability between 0 and 1 and assign pi 2 as the remainder so that they both add to 1. But I prefer a distribution like beta, whose domain is still bounded between 0 and 1, and thus a good choice for sampling probability, but it can take on more interesting distributions, as shown in this GIF. A quick refresher on the beta, the formulation is given here, and you can see how drastically different it can look. The second parameter controls concavity, so low values will cause higher probabilities at the edges, whereas high values will look more like a bell curve. As shown in the middle, you can still get a uniform distribution by choosing both parameters as 1. You can even tweak the first parameter to get a skew, so sampling your beta will give you a value for pi 1 that's consistently close to 0 or 1. Such vastly different pi would mean a sample data point has a much higher probability of belonging to one class than the other. So what if we kept things finite, but expand to multiple clusters? Our data setup looks the same, but now we have k classes and k different class probabilities. Instead of beta, we use a multivariate beta, or Dirichlet distribution, which lets you sample k different values that all add up to exactly 1, thus being a good choice for sampling our class probabilities. With a beta, we were able to find pi 1 and its complement pi 2. Here we want 3 pi's that add up to 1, so they're on this three-dimensional plane you see here, which you might recognize as x plus y plus z equals 1. Check out these heat maps, where a lighter color means a higher probability. You can see the skew parameters where the bottom left image skews to the extremes, meaning one of the pi probabilities will be disproportionately higher than the others. In the middle, setting all parameters to 1 yields a uniform probability of any combination of pi's. And on the right, we see that the hill-type distribution that gives a high probability that all the pi's you draw will be close to each other, which logically peaks at every pi being about 1/3. So how do we choose the number of parameters k to apply to this distribution? If k is too small, we want to account for parameters for certain clusters, and if it's too large, we might overfit the data by identifying clusters that aren't there. And, for a non-parametric approach, how would we even get infinite k? Well, the idea is that we have infinite dimensional parameters, of which only a finite number are realized. Think about continually breaking a stick in half, and discarding the piece you broke off. You can break it in half an infinite number of times, but you only need to break it twice to, say, discard 2/3 of the whole stick. So think of a Dirichlet as a sequence of breaks, which are our betas. The first break is getting pi 1, using a beta with the first parameter and the sum of all the remaining parameters. Then, the remaining pi's are Dirichlet distributed over the remaining portion, which is 1 minus that pi 1 piece we discarded. We can repeat the stick breaking by saying pi 2 is beta distributed across this region 1 minus pi 1. The output of just the beta, let's call it Sj, can be thought of as the portion of the remaining stick that is broken off when picking a given pi j. Repeating these stick breaks, we can assign infinite pi's throughout the range 0 to 1. A simplification of this is the GEM distribution, which assumes each stick break has 1 as the first parameter and the same value alpha as the second parameter. We can adjust this in relation to 1 to either favor really high or really low values, which represent what portion of the remaining stick each pi will break off. Shown below, a higher alpha produces a more even breaking of all these infinite pi's. We manage this infinity by not sectioning off all the class probabilities until we want to assign that particular class. For example, we uniformly draw some value between 0 and 1, like 0.8, then use this sectioning to determine it falls under class 4. This process takes in a parameter for our GEM distributions and a function for generating cluster parameters. First, we draw our random number n between 0 and 1. If we don't know which class this falls into, we repeatedly break sticks until all the pi's we found add up to more than n, so we can assign it a class. Let's look at an example. Say I draw 0.4 randomly, but I don't know what class it falls into. I run a GEM once, and I still don't know. I run it again, and now I know that it falls within the pi 2 probability, so it belongs to class 2. If I draw a 0.1 on the next turn, I already know it falls within class 1. If I draw a 0.9, I now need to run 2 stick breaks in a row until I have the region that 0.9 falls into, which is that of pi 4. Notice the empty space at the end. There's infinitely many pi regions divided up in there, but I don't care about those because I only calculate the regions up to and including whatever samples I've drawn. Now, based on each sample's class, we will use func to give it a class parameter, like a centroid of a cluster generated from a multivariate Gaussian. Then, we'll use these parameters to generate our sample point. Now we move to the idea of random measures, which look complicated, but we can break it down. So we're still summing up over our infinite classes with associated probabilities pi, but now we generalize some terms. So we have a space omega, which we said was the 2D plane up till now, but could be any kind of space, like all possible colors or the entire 3D solar system. Over this space, we have a distribution, and remember we said that the cluster means came from this normal distribution here, so let's say it's centered in the middle of this square. From this distribution, we take a sample phi, which was like our cluster centroids before. All that's left is a Dirac delta, which is an impulse arrow pointing up from phi k with magnitude pi k. Then G isn't really a sum in the traditional sense, but a collection of all these blue measures across the space omega. G is a random because pi and phi are both drawn from distributions, and G being a measure means summing it over a subspace A just means adding up the pi measures within that space. So for that purple area A, G of A would be pi 1 plus pi 2. So this G is actually a stochastic process, which is like a collection of random variables associated with an index set. For example, the stock market is like a stochastic process associated with the index set of time. So if you fix a moment in time, I can give you a random variable, like a bell curve, that represents how the value of a stock will be distributed at that moment of time. In our case, picking the index set as all possible subspaces A in omega from before lets us define our stochastic process G of A as a function that takes in some subspace A and outputs a random variable representing how the sum of the pi measures within A is distributed. This random variable output is what lets us perform Bayesian analysis, as we can refine our parameters of our Dirichlet process by finding what maximizes our conditional times our prior. But what would a prior for a stochastic process look like? We could sample from the distribution repeatedly, or find a theoretical formula for full precision. Let's demonstrate that with the Chinese restaurant process, but I'll briefly cover the idea of a Polya urn first. Imagine you have an urn, or a pot, with the white and a black ball in it. You reach in, grab a ball, and whatever color you picked, you put 2 of that color back in. This is preferential attachment, as the more often you pick white, the more white you put back in the urn, and thus the more likely you are to pick white next time. CRP is a similar preferential attachment model. It's a stochastic process that attaches a random variable to a partition arrangement of a set. For example, for the set of integers 1 through 7, a valid partition would be thus. We'll pretend these inner sets represent customers seated together at a table. Let's say you have n diners walk into a Chinese restaurant in order from 1 to n. After I customers have entered, when the I plus 1th customer walks in, they are preferentially attached to join a pre-existing table based on a number of people already at that table, but tempted to join a new table by some factor alpha. Thus, the probability of them joining a given table is the number of people at that table, say magnitude of t, and the probability of starting a new table is alpha, normalized by alpha plus I, so all the probabilities add up to 1. So what's the probability of a given arrangement? Well, knowing that they came in order, we know Diner 1 had to choose a new table, Diner 2 also had to choose a new table, Diner 3 joined a table of size 1, and so on. Pause if you want to work out the pattern to this yourself, but a clear formula for the probability of a given partition is such. The denominators are a product of alpha plus I minus 1 for all customers, times the numerator, which is a product of alpha for the first seeder and the product of every additional seeder up to the cardinality of t minus 1 for every table set t. This is called an exchangeable partition probability function. The probability is only dependent on the total number of diners and the cardinalities of the tables, or the partition sets, and not who is at what table. Di Finetti showed that if you know this exchangeability about a sequence of random variables, the fundamental theorem of Bayesian analysis tells us that there's an underlying representation G, like that from before, that we can find a probability measure over. If you can imagine a variant of the Polya urn, where drawing a black ball means putting back the black ball and a new colored ball, kind of like the diners picking a fresh new table at the restaurant, it's still exchangeable. As it turns out, the G for this new colorful Polya urn is actually our random measure from earlier, which used the GEM distribution, so that's pretty cool. We use the Chinese restaurant process and Polya urn to show how we can find a mathematical prior for our stochastic process, which we can apply to our Bayesian analysis to predict the probabilities of our parameters or Dirichlet processes. If the math is too involved, you can also use Gibbs sampling or Monte Carlo methods to repeatedly sample the prior formula so you have a vague idea of what the prior distribution is, and then use that in your Bayesian analysis as an estimate. This approach, as opposed to bounding your K and parameter pool, allows you to simulate and capture better patterns in your network, graph, and cluster study. I'll pass it to Andrew to cover how we can apply the techniques we've learned in a variety of fields.
Nonparametric Bayesian finds its applicability in a variety of fields. When someone has a condition that requires medical treatment, health insurance companies are interested in assessing the risks and pricing of that particular condition. Episode treatment groups, or ETGs, are used to categorize these policyholders. Insurance companies would like to know the distribution of costs associated with an ETG given certain conditions about the policyholder. For example, what are the typical costs of treatment for a 50-year-old male with diabetes? Traditional models have tried to simulate the distribution of costs, but have failed because of these strict assumptions that the models hold. Thus, this is where nonparametric Bayesian comes in. These two researchers developed a nonparametric Bayesian method that can model the distribution of costs associated with an ETG given the age and gender of the policyholder. In this figure, total log charges of different ETGs of a male aged 40 are plotted. As shown, the distributions cannot be accurately represented by a common probability distribution. There are multiple modes, and the tail behavior isn't quite as expected. These researchers used an extension of the Dirichlet process called the dependent Dirichlet process ANOVA, which uses realizations from a Bayes stochastic process rather than a Bayes distribution and allows for the inclusion of covariate information. The resulting model can generate any distribution. Inference was done through sampling from the posterior distribution using blocked Gibbs sampling, which groups two or more variables together in samples from the joint distribution conditioned on all of the other variables. To assess model performance, they use the deviance information criterion, which accounts for the distributional accuracy and penalizes for higher complexity. They compared their model to two other models, the Bayesian linear model, or BLM, and the generalized beta model, or GB2. They used the Bayesian linear model to demonstrate how the assumptions for linear models fail when given the data of the ETGs, and the generalized beta model as a more flexible option than the Bayesian linear model. The Bayesian nonparametric model outperformed the Bayesian linear model in every ETG and outperformed the generalized beta model in every ETG model but 11. They chose two particular ETGs to highlight the performance of the Bayesian nonparametric model: conjunctivitis, which had a lot of observations and distributional features that were non-Gaussian, and lung transplants, which had little observations and could not be subsetted into certain combinations of age and gender. This figure shows the different models overlaid with the log charges of all 18-year-old females with conjunctivitis. The Bayesian nonparametric model was able to create a distribution that correctly captured the behavior of the tail, whereas the two other models did not. This other figure shows the posterior predictive distribution for the log charges of different age and gender combinations for lung transplants, with the actual charge being plotted using the solid green vertical line. The charges were able to be within the bounds of all the models, but the Bayesian linear model gives a wider variance and almost looks like a uniform distribution, which doesn't really help when it comes to assessing the probability of a cost. Surprisingly enough, nonparametric Bayesian has a place in medical imaging. Positron emission tomography, or PET imaging, uses a radioactive drug called a tracer that reacts or binds to a tissue or organ to visualize a metabolic process within the body. When the tracer reacts or binds to the target, it will undergo a decay process that fires gamma rays in opposing directions. These rays are detected by a scanner, and the resulting information gets processed in a computer to generate an image. The usage of nonparametric Bayes actually comes in reconstructing the image. Given information about the location of the ray, the time it was recorded, and the density of the rays, we would like to reconstruct an image that shows the distribution of the tracer. What is commonly used is maximum likelihood using estimation maximization, or MLEM. But a drawback of this method is that it's based on an overly simplified model of physical processes, and as a result, induces a lot of noise and bias into the resulting image. The researcher employed a non-parametric Bayesian model that can reconstruct the image. This image is just a schematic of how PET works, but as you can see, the gamma rays shoot off from the area to be visualized and to be recorded by the detector. The researcher employed a hierarchical Dirichlet process mixture, or a DPM, as a prior for the spatial distribution of interest. The rays can be thought of as a cluster that draws from a Bayes distribution. The researcher then used a Markov chain Monte Carlo sampler to generate the random posterior densities. Smoother images indicate better quality. The algorithm was able to generate a high signal-to-noise ratio and good spatial resolution under an artificially lowered dose over MLEM with a regular dose, both the uncorrected and corrected version. It was concluded that from this method, it has several advantages over MLEM. It's independent of any fixed functional form, and it is relevant when working with low doses. As it's shown, Bayesian nonparametric methods are powerful tools for solving complex problems when conventional methods may fail.